I must have done something like 4 or 5 videos by now. But to tell you the truth, we are still into the introductory phase of integral calculus. There is a lot of techniques to obtain the antiderivative of functions. And what we had been doing so far is only illustrating to you or how to do integration using the definition. Okay, so our first definition interpretation is the integral is the area of a function or area of a region bounded by curves. And the other understanding is the integral is the antiderivative. And so we are still into that. We are demonstrating how to do integration by using the notion of the derivative, because the integral of a function is the antiderivative. So these are the linear properties of integral. So the integration is somewhat like an operation. It's something that does something to a function. And it follows these linear properties. It's like if you have a sum of functions, the integral of a sum of functions, sum or difference, is equal to the sum or difference of the integral of each of those functions. So these linear properties, okay, it doesn't apply to a product of functions. If you have the integral of f of x times g of x dx, that is not equal to the product of the integral of the functions. This is just not true, and also for this. So by now, you can see that anti-differentiation, the integral, requires knowing the derivatives of functions. And not only that, anti-differentiation also requires knowing the fundamental trigonometric identities. You know, all teachers, all instructors who teach integral calculus, they assume that you know this. You know the derivatives of functions, which is why differential calculus is a prerequisite for integral calculus. Instructors who teach integral calculus assume that you also know quite a number of fundamental trigonometric identities. I assume that you have this with you, okay? Your knowledge of the basic derivatives of functions and your knowledge of a few of the common fundamental trigonometric identities. I will again demonstrate the idea behind the integral as the antiderivative. Let us find the integral of tangent of x dx. What is that function, f of x, so that the derivative of that function will give you tangent of x? And that's going to be the value of this. Is it the square of cosine of x plus z? Is it this or is it this? Well, in order for us to know which function is the antiderivative of tangent of x, we must get the derivative of the square of cosine of x. And this is equal to, obviously it's not equal to tangent of x. So letter A is not equal to the integral of tangent of x dx. How about letter B? Let us obtain the derivative of this function. Times the square of secant of x. Again, obviously, it's not equal to tangent of x. How about letter C? What is the derivative of this function? 1 over cosine of x, and then the derivative of cosine of x is negative sine of x. And this is equal to tangent of x. So this is the correct function. This is equal to the integral of tangent of x dx. Okay? Tangent of x dx is equal to the negative of ln of the absolute value of cosine of x plus c. How about this? Let us find the integral of the square of tangent of x dx. This time, we will use trigonometric identities. Okay, in the previous example, we used our understanding of the integral as the antiderivative. Now, we will use something else. We will use trigonometric identity. So what trigonometric identity can replace this? And that trigonometric identity is a function whose integral we already know. Is this the identity that can help us with this integral? Maybe this one. Is this the function? Is this the identity that can help us with this one? It looks like it is letter C, okay? Okay, so you are not familiar with this one because usually this identity is written as 1. Okay, this identity is often written in this way. But we can use this, okay? So this means we can replace the square of tangent of x by the integral of the square of secant of x minus 1. Okay, so we will work on this. And we already know using the linear properties of the integral, this is equal to the integral of the square of secant of x dx minus the integral of dx. And we already know this. This is equal to tangent of x and minus the integral of dx, that is just equal to x, and then of course plus c. We already know that the integral of the square of secant of x is tangent of x. Suppose we didn't know that, okay? How can the trigonometric identity help us with finding the integral of the square of secant of x dx? So which identity here would be helpful? So this is true. This is a fundamental identity. So with this one, well, let us try this one, okay? So we can write the integral of the square of secant of x dx as equal to the integral of 1 plus the square of tangent of x dx. Using our linear properties, it is equal to this. Okay, we already know this. This one is equal to x, and this one from the previous slide is equal to tangent of x minus x. X minus x is 0, and so this one leaves us with tangent of x plus c. Working on the idea of the integral as the antiderivative, what we can do is what function will give us a derivative that is equal to the square of secant of x? Okay. Well, that function turns out to be tangent of x. Tangent of x is equal to, okay, sine of x over cosine of x. And so the derivative of tangent of x will require you to do the quotient rule for derivative. Okay? You will square the denominator, so this becomes the square of cosine of x. And then in the numerator, you have this mnemonics. Lo di high minus high di lo. Lo di high. So you will copy cosine of x times di high. The derivative of sine of x is cosine of x. And so it becomes the square of cosine of x plus or minus high di lo. You will copy the numerator, it's sine of x times the derivative of the denominator, which is negative sine of x. Minus negative is going to be positive, and so this becomes the square of sine of x. So I hope that you can recognize this. This is your Pythagorean identity for trigonometry. It is equal to 1. And so it is equal to this. 1 over the square of cosine of x. And of course, you know that to be equal to the square of secant of x. And so there you have it. Okay? I am flashing this small table. There's a lot of trigonometric identities. There's a lot. But for our class, integral calculus, these are the list of trigonometric identities that matter to us. So you must remember this. Okay, so especially the reciprocal and quotient identities. Okay, the Pythagorean identities, you must know this. And this one, double angle identities. Because we will use this whenever we have to obtain the integral of the square of sine of x or the square of cosine of x.